You think of railways as simple transport, A to B. But what if some machines on those rails were engineered at the absolute limit of physics? Weight, over 660,000 pounds, 300 tons, the equivalent of 200 passenger cars concentrated into a single massive engine. These are not trains, they are industrial colossi on rails. They were designed for one purpose, to haul hundreds of freight cars through empty deserts and frozen tundras, operating where conventional machines would simply fail. This reality raises critical engineering questions. What was the single largest locomotive ever constructed? Which specific model required the tracks themselves to be structurally reinforced just to support its immense operational mass? These machines are not fiction. They are real-world answers to moments in history that demanded unmatched power and resilience. Stay with this analysis to the end. The final machine is an artifact from a different engineering era, a giant so old its first run predates the world most of us know. The promised giant from the past has arrived. 1953, South Africa. Meet the Class 25, a steam locomotive that learned to drink its own water to survive. It was built by the North British Locomotive Company in Henschel to solve a single critical problem: the Karoo Desert, an arid wasteland where water was more precious than fuel, and conventional steam engines would die of thirst. This machine was an engineering paradox. Instead of violently expelling its exhaust steam, the Class 25 captured it. The vapor was channeled into a colossal 112-foot-long tender condenser. Inside, giant fans forced air over a web of pipes, cooling the steam until it turned back into liquid. That reclaimed water was then pumped directly back into the boiler, a closed loop, a self-sustaining system. The result was an almost silent giant. Not the percussive blast of a normal locomotive, but a deep, contained hiss from a boiler operating at 20 times atmospheric pressure. The operational range was staggering, nearly 600 miles without a water stop, the equivalent of traveling from New York City to Chicago on a single tank, on steam. But this hyper-specialized technology was also its weakness. The complex system was a masterpiece of adaptation, but only necessary for a single punishing environment. Once the locomotives were reassigned to routes with abundant water, the sophisticated condensing gear was removed, converting them into the simpler Class 25 NC. The ultimate survival tool had become dead weight. The Class 25's elegant solution was steam's final masterpiece. But this is the diesel era's reply from 1995, the GEAC 6000 CW, a machine where the bet was placed not on engineering finesse, but on absolute crushing power. 6,000 horsepower. At its core lay the purpose-built 7HDL16, a massive V16 engine. It spun a primary alternator to generate immense alternating current. That current then powered individual traction motors on each axle, creating colossal force. The machine weighed 432,000 pounds, a rolling fortress of steel designed to pull the heaviest loads across a continent. Its output was equivalent to the combined power of 12 Formula One race cars. At full throttle, it didn't just make a sound, it produced a rolling thunderstorm, a deep, continuous, low-frequency rumble that vibrated through the ground itself. This was the peak of the horsepower wars, a race for a number on a specification sheet, but the reality on the tracks was different. The very engine that gave the AC 6000 CW its record power was also its fatal flaw. The 7HDL16 proved complex, unreliable, and notoriously thirsty for fuel. Railroads saw operational costs spiral. The power was immense, but the price was too high. The production run was short. In the end, the industry replaced the giant with more modest 4,400 horsepower models, a compromise that proved far more profitable than the record. But if 6,000 horsepower in the AC 6000 CW proved excessive for a single module, Chinese engineers in 2004 found a different application for such power, creating the DF11G, a locomotive made of two inseparable parts. This is not a story of brute force. This is a story of engineered purpose. China's challenge, moving massive passenger trains at high speed across vast, non-electrified territories. Their solution, built by Qishuyan Locomotive Works, was the DF11G, a twin-unit diesel-electric machine, 2 engines, 1 locomotive. The sheer scale is immense. The two permanently coupled units stretch 144 feet, almost half a football field of steel and power. Together, they generate over 6,400 horsepower. The goal was not simply raw tractive effort, but sustained velocity. The design allows it to exceed 100 miles per hour, making it one of the fastest diesel passenger locomotives ever built. Where American gigantomania placed all its power in a single monolithic frame, the DF11G distributes it. This composite system provides the stability needed to haul long passenger consists across China's enormous network, connecting cities like Beijing and Shanghai, where electrified lines were not yet complete. It is a pragmatic solution to a specific infrastructural problem, a workhorse, not an experiment. DF11G is the pinnacle of the standard approach to diesel traction, but there are machines created not for main lines, but for extremely narrow, niche, and experimental tasks. If the previous locomotive was an example of mass-produced pragmatism, the Soviet AA20-1 is its polar opposite. This was not just an experiment. It was an engineering manifesto where practicality was sacrificed to an ideology of gigantism. Its key parameter, the 4-14-4 wheel arrangement, became both its triumph and its death sentence. A standard heavy freight locomotive of the time used a flexible frame with perhaps 10 driving wheels. The AA20-1 used 14. 14, a single rigid line of steel. This 550,000-pound machine stretched 135 feet, the length of 8 Volkswagen Golfs parked end to end. Its entire frame was engineered as one inflexible beam, designed for a singular purpose, moving in a straight line. On any standard railway curve, the physics became impossible. The 3D models show the core flaw. The rigid chassis simply cannot follow the track's changing radius. The inner and outer wheels fight the rails. The result is a catastrophic grinding, the shriek of steel wheel flanges biting into the track, fighting a battle they were engineered to lose. Built in 1934, the logic behind the AA20-1 was to distribute its immense weight across more axles, increasing tractive effort for colossal freight loads. Its power plant produced approximately 4,200 horsepower, but this machine was not about pure output. It was about axle count, a record. From its very first run, the design proved to be a functional disaster. The locomotive was too long for existing turntables, too heavy for many bridges, and fatally, too rigid for the Soviet rail network's curves. Every attempt to operate it outside of prepared test tracks was a mechanical struggle against basic geometry, a practical failure. The project was quickly abandoned. The pursuit of a world record had created a locomotive that could not function in the real world. The sole unit ever built never entered regular service, standing today as a monument to engineering overreach. The Soviet AA20-1 was a victim of ideology, but just 5 years later, in 1939, the United States created an equally grand and impractical machine. Here, the bet was not on ideology, it was on aesthetics. Enter the Pennsylvania Railroad S1. This was a locomotive conceived as a piece of art, sculpted by industrial designer Raymond Loewy. He draped the engine in a sleek, flowing Art Deco shell, hiding the complex mechanics under a skin of polished metal. Its appearance was a radical break from any steam locomotive that came before. It was beautiful, and it was a beast. Underneath the streamlined fairings lay a duplex drive engine with a 6-4-4-6 wheel arrangement, a configuration generating over 6,500 horsepower, but its power was constrained by its physical form. A rigid frame stretched 140 feet, a crushing weight of over 575,000 pounds. Just like its Soviet contemporary, the S1 was too long and too stiff for the very network it was built to serve. The giant was trapped. At the New York World's Fair, it was a sensation, running on rollers under its own power as a vision of the future. On the actual rails, it was an operational liability, unable to navigate the tight curves of yards and secondary lines. The pursuit of a perfect aesthetic had created another perfect failure. The S1's service life ended after only 7 years. In 1946, despite its status as a design icon, the single prototype was ruthlessly cut apart for scrap. The era of steam giants, defined by aesthetic ambition and brute force, ended with their dismantling in the mid-20th century. More than 70 years later, Siemens introduced a new giant, the Vectron dual mode. But here, complexity is not a monument to power, it is a precise economic calculation. The core problem is the last mile of European freight. A train travels hundreds of kilometers under electric catenary only to arrive at a destination, a port, a factory siding, with no overhead lines. The result is a mandatory locomotive swap, a costly delay for the final final segment of the journey. But why build a single complex machine instead of simply using two? Because time is the currency of modern logistics. The Vectron Dual Mode, launched in 2020, is the engineered answer. It integrates two complete propulsion systems within a single frame. One system is a high-voltage converter, drawing power directly from the grid for mainline operation. The other is a self-contained diesel power plant. Two systems, one frame. This diesel unit is a 16-cylinder V engine, a dedicated solution for non-electrified tracks. It allows a heavy freight train to detach from the electric network and continue its journey seamlessly, eliminating the need for a second locomotive. The problem is solved. The supply chain is unbroken. Its diesel plant generates a formidable 3,200 horsepower, but this is merely the entry point. The Vectron's 3,200 diesel horsepower is a solution for the plains of Europe, but for the Malmbanen line, deep inside the Arctic Circle, an entirely different class of power is required. There, where temperatures drop to -40 degrees Celsius and a single train weighs 8,000 tons, the mission demands a system delivering over 10,800 horsepower from pure electric traction. This is the Bombardier IORE, a machine engineered for one purpose: to conquer the extreme. Unveiled in the year 2000, it operates on a single vital route between Kiruna, Sweden and Narvik, Norway. Its design is a direct response to the brutal physics of its environment. The structure consists of two permanently coupled units, a configuration that distributes its massive weight and maximizes adhesion. 12 powered axles, 6 per unit, bite into the icy rails, fighting for every inch of grip. The scale is immense. An empty, snow-covered plain stretches to the horizon. Then, a point of red appears, growing into the twin-section IORE, pulling an almost endless chain of cars behind it. The total weight of this moving convoy can reach 8,000 metric tons. That is the mass of the Eiffel Tower, sliding across the frozen tundra. The locomotive itself moves with the near-silent hum of high-voltage electric motors, but the train it pulls generates a different sound. A deep, low-frequency rumble that travels not through the air, but through the frozen ground itself. This is not an exercise in breaking records. It is a critical economic artery. Each IORE locomotive is designed to travel over 2.5 million miles in its lifespan, pulling the iron ore that fuels a key Scandinavian industry. Its power isn't just massive, it's clean, drawn from local hydroelectric sources. A perfect fusion of brutal strength and modern efficiency. Its singular task is to haul thousands of tons of ore through a landscape of ice, and after the train passes, absolute silence returns to the Arctic tundra. The IORE electric locomotive was built for the Arctic extreme, but in 1941, a different geography demanded an entirely different kind of power, moving thousands of tons of coal through the mountain passes of the Appalachians. This was the singular task for the Allegheny H-8. The engineering problem was immense. The Chesapeake and Ohio Railway needed to haul colossal loads up steep grades and through tight curves. A single rigid locomotive frame of the required length would derail. The solution was articulation. The Allegheny's chassis was essentially two engines joined under one massive boiler. A forward set of 6 driving wheels pivoted independently from the rear set. This allowed the 540-ton machine to negotiate mountain curves that would break a conventional design. In those turns, the air filled with the low-frequency screech of steel wheel flanges grinding against the inner rail, the sound of a giant under stress. Its power source was a firebox larger than a family car, heating a boiler to an operational pressure of 300 pounds per square inch. The result was 7,500 horsepower. This was not an exercise in breaking records. It was a cold calculation of force. The H-8 was designed to haul a 160-car train without assistance. That's a total weight of over 14,000 tons, stretching more than 2.5 kilometers. One engine for one task. It was the absolute peak of specialized steam engineering. A brute force solution created just as its era was ending. Despite its power, the Allegheny was a dying breed. Within 15 years of its debut, the Chesapeake and Ohio Railway had fully converted its mainline operations to diesel. The Allegheny H-8 reached its 7,500 horsepower from a single giant boiler, the peak of extensive development. But by 1969, engineers at General Motors demonstrated a fundamentally different approach. Instead of scaling up one massive engine, they combined two two serial production V16 diesel engines to create the most powerful single-unit diesel locomotive in history. The result was the EMD DDA40X, nicknamed the Centennial. The engineering logic was compelling. Union Pacific Railroad sought to replace its standard double-heading configuration, two locomotives operated by two crews, with a single ultra-powerful unit. Inside the DDA40X's 98-foot frame sat two separate 16-cylinder prime movers. Each generated 3,300 horsepower, a combined 6,600 horsepower. This dual-system architecture, however, was its fatal flaw. The locomotive was two independent power plants fused into one chassis, creating a maintenance nightmare. Two engines, two electrical systems, double the potential points of failure. Union Pacific commissioned 47 of these giants to mark its 100th anniversary, deploying them on the most punishing routes. But the promise of efficiency was undone by reality. The high operating costs and mechanical complexity proved unsustainable. Most of the fleet was retired after just 15 years of service. While the complex dual-engine system of the DDA40X proved an economic dead end, steam engineers made one final colossal bet on ultimate reliable power. They created a locomotive whose name, scrawled in chalk by an anonymous worker, became synonymous with engineering greatness: the Union Pacific Big Boy. It was designed with a single brutal purpose: to haul immense freight loads over the steep grades of the Rocky Mountains without assistance. This required a machine of unprecedented scale, a mass of over 1.2 million pounds. That is the equivalent weight of a fully loaded Boeing 747 airliner. From coupler to coupler, it stretched 40.5 meters long, built to deliver approximately 6,300 horsepower from a single gargantuan firebox, the apex of steam. But its era was brief. By the late 1950s, all 25 big boys were retired, replaced by more efficient diesel electrics. For over 50 years, they were silent monuments. In a California park, locomotive number 4014 sat exposed to the elements, a rusting hulk. Then, Union Pacific engineers launched one of the most ambitious restoration projects in railroad history. They began the slow, painstaking process of bringing the giant back from the dead. Engineers crawled inside its cold firebox, meticulously rebuilding the boiler system that had been dormant for half a century. They machined colossal new components and reassembled the articulated frame piece by agonizing piece. In 2019, the work was complete. Its first test firing sent a shockwave through the rail yard, a low-frequency vibration that traveled through the solid ground felt in the body hundreds of meters away. It was no longer a museum piece, it was alive. This resurrection, however, reveals the critical truth of steam power. The cost of restoration was astronomical, and its current operation requires a dedicated team and a budget that renders it economically unviable for commercial freight. It is a living icon, but also a financial black hole, a rolling monument to a bygone engineering philosophy. Today, it thunders across the continent on special tours, a rolling earthquake of steel and steam. The big boy roaring on the rails today is not just a machine. Its rival, the Allegheny H-8, and the diesel giant DDA40X Centennial are all monuments to engineering philosophies frozen in time. The steam titans were an exercise in brute force. Their logic was founded in the firebox, a direct and violent conversion of thermal energy into mechanical torque. More power meant more fire, more steam, more pressure. A raw physics problem solved with overwhelming force. Fire, steam, steel. The DDA40X Centennial was a different argument entirely. It was not a locomotive, it was a mobile power grid, a complex integrated system where diesel engines didn't drive the wheels but powered generators, which in turn fed electricity to traction motors. A solution built on efficiency and control, data, circuits, kilowatts. These machines are physical records of a fundamental debate, one born of raw, explosive power, the other of calculated systemic efficiency. Which philosophy ultimately builds the modern world?